suppose if you are having a Dirac delta function, let's say it's v of x, it's equal to minus s from the delta of x. So let me give an example. Okay, so this as an assignment so that you can do it at your paper. So it's like this thing. I mean, these are very sharp. Yeah. So this is your delta function because it's a negative sign. That's why peak is downwards. If it's a positive sign, peak is upward. Okay. So you have to calculate the s plus plus for this object. So you need to calculate. If you know s plus plus for this very problem, what you can calculate bound states. So do this problem in this way. I will give the hint how to go for it. First, when you are since you are having this very potential, it is defined by this delta x. There is a singularity at x equal to 0. Potential goes infinity, is it? When you put x equal to 0, what happens delta of 0? That's infinity. It's not a discontinuity, it's an infinity. It's a singularity. Clear? So when you are having such kind of potentials where you feel singularity in some region, although wave function is continuous, but the first derivative of wave function is discontinuous. Clear? Okay, so you are having the wave function here, psi is continuous, okay, but d psi by dx is discontinuous. So how much is that discontinuity? Okay, so it's like this thing. Let's put limit of epsilon tends to 0 plus, okay, d psi by dx. You have to evaluate it as x is equal to, let's say, epsilon in the region here, epsilon and minus epsilon. Clear? Okay, in this very region. Okay, minus d psi by dx evaluated where x equal to minus epsilon. This much is actually equal to twice m. Okay, v. Okay, so it will be minus. Since this is a minus here, it will be minus twice m by extra square alpha psi evaluated at the point where there is a discontinuity. Okay, at the point x there is a discontinuity. I will be doing this problem but for a double well potential in a moment. But you have to do it for this potential. Okay, so you have to take the scattering states. What you are having? So you are having a left region and right region. Take even parity states. So you know the psi plus here and psi plus here. You know that. What is our, I mean the scattering states? Tell me. So you are having the psi plus is equal to that I plus S plus and O plus. Is that true? So that is something equal to e raised for I kx plus S plus e raised for minus I kx in the region x tends to minus infinity and e raised for minus I kx plus S plus e raised for I kx in the region x tends to S infinity. Only you have to do match these two wave functions where at x equal to 0. Okay, so the continuity will yield you nothing. Okay, let's take at x equal to 0. It will be 1 plus s plus plus is equal to 1 plus s plus plus. It will give you nothing. Okay, only the non-trivial things will come from where? From the derivative. Okay, let's just calculate the derivative of this thing, derivative of this thing, make the difference. Clear? At x equal to 0, put it equal to psi of 0, 0 and solve the equation, result equation for what? S plus plus. Once you figure out S plus plus, what you get? That means you have got the scattering amplitude. Clear? Or the scattering matrix you have got. Okay, find the poles of that matrix, what you should get? Energy. Clear? So you will get energy is actually equal to, what was that? H cross square. So it is H cross square lambda square by twice m. Is that true? You will figure out lambda. Huh? Okay, what is lambda? K is equal to I lambda. This is the rule. Okay, you have to figure out the poles of the S matrix where when you put K is equal to I lambda. Clear? And figure out what is the lambda. Substitute it here. You will get exactly minus m alpha square by twice H cross square. So there is only one bound state and having this much of energy. Clear? So this only one Dirac delta function is having this. Clear? So this is the hint how you have to solve it. Okay. So now let's Okay, so let's try to understand the concept of the resonance. Resonances are what we call the metastable states. These are actually unstable states, are the unstable solutions of the Schrodinger equation. Okay, so let's consider this kind of potential. Okay, so this is our potential, and it vanishes in the asymptotic region. Clear? Got it? Now let's put a particle in this very case. So you are having a particle described by some wave function. Let's think classically. What will happen to this very particle classically? So it will execute motion within that very potential, and it will not leave the potential unless and until the energy of this particle is greater than the barrier. Clear? So it will only then leave this very potential. Clear? But quantum mechanically it's not true. There is something more to it. Okay? So let's assume if the barrier height is very large. Clear? So let's assume these are rigid barriers and it's very large. A particle that's confined within this potential, think of simply potential well. Okay? A particle confined within that, it will always stay there. Clear? Okay. Now if these barriers are not rigid, what will happen? This particle will stay for some time here in certain state. But ultimately it will leak out through the potential. That means it will tunnel through this potential, and there will be a finite probability of figuring out the particle outside this barrier. Got it? The state in which this particle exists for some time, which is hence some finite lifetime, those states we call as the metastable states. Got it? Now, or we call them as the resonances. These are very important objectives in physics. Let's say if you have to discover a new particle, how you do that? It is because, let's say, recently you have heard about the discovery of the Higgs boson. How we have discovered it? It is through actually resonances. These particles stay in a given state for a shorter time. Okay, let's say it exists as a resonance. Let's say if a particle gets formed, and if it's very short lived, so that means it will decay out of that state. And you have to observe that resonance. If you know that resonance perfectly, that means you have discovered the state, or let's say here the particle. Got it? So they are very important. Now how to describe, okay, from from the S matrix, how we describe these resonances or these metastable states. Okay, so you know these metastable states from actually lasers as well. Okay, you create, let's say if you have to a working laser, if you need a working laser, for that matter you figure out what is the metastable state and you populate that state. Clear? Okay, so that although that is that's a short-lived state. That's not as, let's say if you are having a particle going from one state to the another state, it will come down immediately, a spontaneous emission. It's okay, so that it is completely unstable in the excited state. But if it goes to some another state which is having some lifetime, but still, okay, the particle will come down. Okay, a tunnel out of that very state. Those states we call as the metastable states. That is okay. So this is actually the description for the metastable state. Got it? Okay. So now let's look into the mathematics, how we can describe these kind of state. Okay. So let's assume. Okay. So we are considering the even potentials here. Okay. So I am considering v of x equal to v of minus x. Okay. So this is our description. Now let's restrict it to the parity even states. So let me take the parity even states. Got it? Okay. So assume. So we assume S plus plus has a pole that lies on the complex plane. Okay, complex momentum plane at, let's say, k is equal to some k naught minus I gamma. Okay, I gamma is some number. Okay, like this thing. So where I have put it, let's say this is your momentum plane. Okay, so this is real momentum. Okay, so this is the real k and this is the imaginary k. Clear? So I am putting it here. So this is our pole. So this is our k is equal to k0 minus I gamma. So I have made it imaginary. Huh? Instead of making it purely imaginary, I have made it complex. Got it? So now you know, since this will be the root of the equation, okay, a dispersion relation described by the Schrodinger equation. So if you are having one root, complex roots come in the conjugate forms. Got it? So that means there must exist another root where? So there should be one another root as k star is equal to k naught plus I gamma. Got it? So much sure? So but we'll restrict it to this very root. Huh? So the same interpretation lies there. Huh? Okay. So now let's try to interpret this root. What exactly it means. For that matter, I will calculate energy of the particle. Got it? If I know this thing, let's say you are having the singular charge or the pole here. Okay, so let's calculate what is the energy corresponding to this pole. Samashaman? Okay, in the yesterday's lecture, why we had the pole? We had pole on this case, on the imaginary axis, and we have calculated the energy to be negative, E less than 0. So that gave us the bound state. But here the pole is somewhere here. Let's understand what exactly it gives me. Okay, so let's calculate the energy. So we'll calculate the energy. So what is that? E is equal to extra square k square by 2f. So what is k? So k square is, so it will be k naught square minus gamma square minus twice I k naught gamma. Clear? Is it? So what we get? So in other words, or I can write this E as some E naught minus I this gamma by 2. Just what will be E naught? It is the real quantity out of this thing. Let's calculate E naught. So it is simply extra square by 2m k naught square minus gamma square. What is this capital gamma? So it is simply twice. Okay, tell me. K naught gamma extra square by m. Okay. So from there, so just read it like this thing. Now what you have got? What you have got? So you have got energy, is it? Energy is complex. So does it feel weird? Can energy be complex? Huh? Classically, it's not possible. So we have to ask quantum mechanics what it gives us. So it is weird, isn't it? So you have got a complex energy for a particle. Okay, so that means a particle described by this kind of momentum is having the complex energy. We need to interpret exactly what it means. It's not unphysical, it is physical. So it has a meaning. So let's calculate the meaning. Let's try to interpret this thing. Okay. So how we write the wave function? Let's say if you are having a time, if you have to figure out the time dependence of the wave function, how you do it? So let's say you are having some state vector psi. Okay, a state of the particle is described by psi. Okay, at certain time, how you write it? So you write it essentially e raised power minus I e t by h cross and psi of x. Clear? So this is how you put, let's say, the eigenstate of the Schrodinger equation, and you attach the time dependence to that. So this is the time dependence of a given wave function. Let's say a particle that is described by that point in the complex plane, I can write its time dependence in this fashion. Okay. Now let's substitute. Okay, this energy. So it goes as, okay. So now let's write it. So what it means? So it is e raised power I. E will be what? By h cross. Okay, e naught minus I gamma by 2 psi of x. So how much is that? So it's e raised power minus I e naught t by h cross e raised power minus gamma by 2 h cross, okay, t psi of x. Clear? So that means, now look here. Okay, so let's forget this very time for the time being. Okay, so let's forget this exponential where there is no I. So you still have this exponential factor. It's an oscillating factor. Okay, but there is this fine. Okay, so this object exists there. So let's say if t tends to infinity, what happens to it? Or let's say t is very large. That means over a longer period. Okay, so you are having this potential. Let's say. So if it leaks out of this very potential and you are observing it for a longer time, what will happen? So it will diminish. So it will decay out. Clear? Okay, so when there will be the effective decay of this very particle, this state. So let's say when t is equal to the inverse of this very object. Okay, so it will reduce to 1 by e factor. Clear? So you got my point? So in other words, the complex root here, the complex part of this very object gives you the damping effect of the wave function. You got my point? When the wave function gets damped out, what happens? What does that mean? So it decays. Over a period of time, it decays. So in other words, the state itself becomes what? So it becomes a metastable state. Got it? And the amount of this damping will give actually the lifetime of that very state. So how much will be the lifetime? Okay, so if I define now, let's say, so lifetime will be how much? So t is equal to twice h cross by tau. Okay, so now what it will be? So it will be simply 2 by h cross t. So it will be equal to e raised power minus t by tau. So that means when t becomes tau, the decay is effective by how much? 1 by e factor. Got it? So that is a sufficient amount of decay. That's how we define the lifetime of a particle. Got it? Or the lifetime of a state vector. So that means a state that is described by the complex energies have actually what? A decaying nature. Okay, so or in other words, they represent the metastable states. The real part of the energy will give you simply the energy of the particle. Got it? And the imaginary part will give you simply the lifetime of the particle. So this will, okay, so what is the lifetime? So the inverse of this object is the lifetime. If you look at the uncertain, what are the dimensions of this tau? It should be energy, because this is energy and energy. Clear? Okay, so what should be by uncertain relation? So it's 1 by energy. Got it? So the h cross is here to adjust the dimension of this tau to be time. Got my point? Everybody followed it? Huh? Okay. Have you got the idea of a metastable state? Okay. So that means this very state, okay. Let's say if you take this gamma tends to 0, where this will go? This will go here. Got it? So, but if gamma is finite and you are observing it for a longer time, where it will go? Where it will go? It will end. No, what will happen? No, yes. Tell me, what will happen to this very point? So when, okay, so what I am saying, this gamma is related to this gamma. Clear? So it means if this becomes very large, what will happen? So this tau becomes 0. So what it means? It becomes an unstable state. Got it? So there is no lifetime for that very particle. So it becomes completely unstable. Now let's say if this gamma is small. Okay? So if this is very small, if this gamma, okay. So if this gamma is very small. So let's say if this gamma approach to 0. So if this gamma approach to 0, this gamma approach to 0, this becomes infinity. Clear? So you know, let's say, what is the lifetime of the stationary states? So it is infinity. So a particle in a given stationary state will always stay there. Got it? So that means the poles on the real axis will give you the stationary states. Samajh? A pole on this very axis will give you what? A bound state. Samajh? So on this very object, you will be having a bound state. But a pole that exists in the complex plane somewhere, which is having a finite value of this imaginary part, okay, will give a metastable state. That can be highly unstable state, or that can be having some stability. A stable state will also be there. Samajh aaya? Okay. So let's take the example of the double Gauss potential and try to calculate this lifetime of a particle in that. So let's illustrate the resonances by double Gauss potential. Sorry, double delta potential. It is an artificial problem, but it's having profound implications. So let me take this V of x is equal to some V naught delta of x plus 1 plus delta x minus 1. What does it mean? So what is the potential? So it is something like this thing. So that is x equal to minus 1, infinity, and x equal to plus 1. Got it? So what is the height? So it's V naught. Samajh? So the weight, this V naught gives you simply the weight of this very potential. Okay, so it will simply, in other words, you can think this V naught will give the strength of this potential. How weak this potential is, how strong this potential is. You can tune this V naught. Okay? So, in other words, you can think this as whether this line is thin or thick. So, imagining it. Okay. So, now let's say you are having a particle here. Okay? So, we are having the same case. The V of x is V of minus x. It's an even potential. So that means if you are having a particle here, it will stay here for some time and ultimately it will tunnel out of this very potential. So let's try to extract the lifetime of that very metastable state. Let's try to understand how we obtain it from the S matrix. Got it? Okay, so I have told you. So once you do the Dirac delta function for a bound state, so you'll observe many things what I will be doing here. So okay, so what are the boundary conditions? So psi, okay, so I will be taking only the even parity states. So let's take only the even parity states. You can take odd parity states. So, and I will choose a boundary condition only at which point? At x equal to 1. So when I take the parity states, so the boundary condition at this very thing is implied. If you don't consider the parity basis, then you take the boundary conditions at both the points. Once you are having a symmetric kind of potential, just choose a boundary condition at one point. Okay, and match the symmetric states on both sides. So you are having, I will take a parity symmetric state here. Okay, let's say even state and same even state here, and match the boundary condition at x equal to 1. Okay, got it? Okay. So let's say, okay, so psi is continuous. So we will choose boundary condition at x equal to 1. Okay, continuous at x equal to 1. What does that mean? So I need to check what is the wave function here. So I have to choose a symmetric here and symmetric wave function here. Got it? Okay, now tell me what is the value of potential inside? 0. Okay, value of the potential is finite here. on these lines. Inside is 0 and here it is 0. So I have to look at the scattering states. Got it? Samashivan? So now tell me what is the wave, okay, what should be the wave function here? So it should be an even function, clear? So what is the solution of the Schrodinger equation here? So it will be some e raised for I kx plus e raised for minus I kx. Okay, let's say you are having normalization constant A. Got it? समझ आओ? Okay. Last time in the potential step, the step potential we have put Q, is it? Got it? So because you had actually that as a finite potential, eh? So you are having a finite extension of the potential there. Eh? So that was the potential within that box was V naught. Eh? But here you don't have V naught within the box. So you are having only V naught at the ends. So last time we had e raised for I qx plus e raised for minus I qx times A. So why this q square was what? Twice mv naught by extra square plus k square. But v naught inside is what? 0. So that's why you use only k. Okay, now tell me what is the symmetric part of the wave function here? Okay, so it is actually, so I have to choose on the right hand side. Eh? So it will be what? Anybody? So e raised for minus I kx plus s plus plus e raised for I kx. Got it? Clear? Okay. So now let's do it. Okay. So when you are having wave function continuous, what does it mean? So it means, okay, now tell me. So e raised for minus I k plus s. So I will put s plus plus here to just differentiate between. So otherwise you will be having plus plus here. You will say why two pluses are there. So you are having e raised for I k. That's called a times e raised for I k plus e raised for minus I. Clear? Got it? Okay. So what it gives me? It yields me a. So what this object is? So this object is actually twice cosine of k. Got it? So it means a is equal to e raised for I k plus s plus plus e raised for I k by twice cosine of k. So this will give you simply the normalization constant a. Got it? Now what is the second condition? d psi by dx is discontinuous, okay, at x equal to 1. Got it? So what does that mean? That means I need to calculate limit of epsilon tends to 0, okay, d psi by dx evaluated at x equal to 1 plus epsilon, because the point is 1 here, x equal to 1, okay. So in the neighborhood here and in the left neighborhood, clear? So d psi by dx, okay, x equal to 1 minus epsilon. So that's actually equal to twice mv naught by h cross square psi evaluated at the point of singularity or the discontinuity. So that is x equal to 1. Got it? Everybody? So now let's take d psi by dx on x at x equal to 1 plus epsilon. So that means I have to choose this very thing. Eh? समझ आवा? Okay, so let's do it. So you are having, okay, when I put even epsilon tends to 0, let's first calculate d psi by dx from on the right hand side. So it's minus I k e raised for minus I. It will be x plus 1 plus epsilon and you put epsilon equal to 0. So it will be simply minus I k. Then you are having plus I k s plus plus e raised for I k. Okay. So this is the d psi by dx evaluated at x equal to 1 plus epsilon. And you have put epsilon equal to 0. Minus, then you are having on the left. So it is a. Okay. So let me write a. Then what you are having? I k e raised for again I k. Clear? X equal to 1 minus epsilon. Epsilon equal to 0, it is 1. Then you are having minus I k e raised for minus I k. Got it? So that's equal to twice m. So let's call this object as u naught. So let's define this as u naught. Okay, so to simplify things, okay, so this is u naught and psi at x equal to 1. So if you look at psi is equal to x equal to 1, so it will be either this thing or that thing. So I will use this thing. So e raised power, okay, so e raised power minus I k plus s plus plus e raised power I k. You can use equally the other thing. Okay. So what is psi equal to? So you have to evaluate psi where? At x equal to 1. So now tell me at x equal to 1 what is psi? Either this a e raised power I k or this thing. Because there is a normalization constant, I don't want to get all these messy factors. So I will use this side. This okay. So now what you are having? So use a. So where you are having a and club the terms. So you are having s plus plus s plus plus s plus plus. You have to club the terms of s plus plus and the rest of the terms. Can you do it? Shall I do it? Okay, so let's do it. Okay, so what you are having? So it's minus I k e raised power. Let's take I k out everywhere. So you take I k out. So it's minus e raised power minus I k plus s plus plus e raised power I k. Okay. Then you are having minus a. What is a? E raised power minus I k plus s plus plus e raised power I k divided by twice cos of k. So multiplied by, once you take actually I k out, it is e raised power I k minus e raised power, that is sine. That is twice I sine. So that's actually equal to twice I sine of k. That's equal to u naught e raised power minus I k. So I will divide this by I k. Because once you take I k out, I have divided it on the other side. Plus s plus plus e raised power I k. So now let's take s plus plus term. So you are having s plus plus here. So it is e raised power I k. Clear? If you see, every s plus plus term has an e raised power I k. E raised power I k, e raised power I k, and e raised power I k. So let's take it. So let's take it out. So what remains there? So it's 1 here. Then, now tell me, minus, okay, 2 and 2 cancels. I sine by cos is 10. Okay, 10k. Then you are having u naught by I k. It's plus on this side. When you take it on the other side, it's minus u naught by I k. Okay, so that is equal to, so you are having u naught by I k. The rest of the terms are having e raised power minus I k. Clear? So then you are having this minus. So let me take e raised. Okay. Okay. So minus and minus, it is plus. So it is 1. Then what you are having? This object minus. So it is plus I tan of k. Clear? E raised power minus I k. Got it? Samashiva? So what you are having? So therefore, this s plus plus is equal to u naught by I k plus 1 plus I tan of k divided by, okay, this thing 1 minus I. So let me write it as minus u by I k plus 1 minus I tan of k. Then you are having e raised power minus twice I. Now if you see for, okay, so this is already a phase factor. So this is conjugate to this thing. So when they are conjugate of each other, that means it's a phase. So that's what we have understood, this s plus plus has to be a phase. So now let's put it in the exponential format. So you evaluate this tan of k. So it is sine of k by cos of k. Clear? So you put sine as e raised power I k minus e raised power minus I k and so on. Clear? So just substitute for that. So ultimately you will get like this thing. And simple rearrangement of the terms, you will get this formula. E raised power minus twice I k, okay, 2k minus I u. So I have actually taken this I up and you multiply k through e raised power ik minus iu e raised power minus ik divided by plus iu e raised power minus ik plus iu naught. Clear? Got it? So now let's look at the poles of this way. First, let's look at the poles. Okay? So let's look at the poles of this problem. Where are the poles of poles of S? So where are they? 2k plus iu naught e raised power minus ik plus iu naught. Since we are looking for which states? Metastable state. That's why we will not put k equal to I lambda. Okay? Samajh aa? Okay, if we have to look at the bound states, just put k equal to what? I lambda. So we will be actually arriving the bound states as well from this problem. Okay, without looking at k equal to I lambda. Okay, in a moment. Okay. So what you are having therefore? E raised power, okay, twice ik. So that's equal to 2k by minus iu probably plus minus 1. Okay, so when you take it on this side, it is minus iu. It will divide this thing up. So it's minus 1 and it, or I will be having e raised power twice ik. That's equal to, let me take minus 1 outside. It's 1 minus twice ik by u. Okay, now look here. It's actually a transcendental equation. I need to solve it for k, clear? Because the variable k we are looking for, the values of k will give actually the energy values, is it? So it's a transcendental equation. Now what we will do, we will make certain approximations first. Okay, so let's take first case. If u naught tends to infinity, so what that means? V naught tends to, it is very large. So the weight of the Dirac delta function is what? It's very large. So that means you are having rigid barriers. Okay, at 2 points, at x equal to 1 and x equal to minus 1, you are having rigid barriers. So what will happen to this very equation? So when u tends to infinity, so this goes to 0. Clear? So what you are having? So it means e raised power twice ik, that's equal to minus 1. What that is equal to? E raised power 2n plus 1 I pi by 2. So, sorry, I pi, not pi by 2. That means odd multiplies of what? Pi. Clear? Okay. So what it gives me? So it means k is equal to 2n plus 1 pi by. So or I can put it like this thing, k is equal to some values of, okay, so n is equal to 0, 1, 2. So what it means? So I'm having a discrete value of what? K. So when you are having discrete value of k, what you will get? Energy? You are getting actually a bound state. Okay? So this implies what? A bound state of the, that is why you are having a rigid potential. Okay, a particle will not leave the potential at all. So it is simply you are having a potential well. And if you see, you have got only what states here? Even states having this much of energy. If you solve, let's say, a symmetric potential well, okay, if you know the calculation of the symmetric potential well, okay, let's say you are having minus a and plus a, and this goes to minus infinity plus infinity. Clear? So much of potential well. For a symmetric potential well, you solve for both even and odd parity. Got it? Even parity solutions will yield you this much of energy, and odd parity solutions will give you an energy which is having 2n here instead of 2n plus 1. Got it? So that you will get the entire spectrum of the problem. Samajh? Yes, sir. Okay? Okay. So now if you take n equal to 0, So let's take n equal to 0. What you'll get? So k0 as simply pi by 2. What is this k? It's actually equal to root of 2me. So therefore energy is equal to h cross square. So what is that equal to? So there should be since a is equal to 1 here, so which one? A is equal to 1. So h cross square k square by just tell me
Divided by 2m.
2m. So what is that? So it is h cross square pi square divided by 2m and 2 square. So it should have been actually like this thing. E is equal to pi square h cross square divided by 2m 2a whole square. Because I have used potential at x equal to 1 instead of a. Samajh? And x equal to minus a. X equal to minus 1 for x equal to minus a. Got it? So it's like this thing. What you have got? You have got the ground state energy of the potential well. Samajh? So how it looks like? So it is the same thing. So you are having the rigid potential without node. So this is your n equal to 0 state. That is what you are having for the well. Got it? Okay. So now let's look. So this is only the case. These kind of states arise when this u naught tends to infinity. Is it? Samajh? So now let's say if this u naught does not tend to infinity, it is finite. It is large but finite. Clear? Samajh? So what to do in that case? So it will admit actually a metastable state. Okay. If you are having finite, second case, finite u naught. Got it? So in other words, finite u naught means finite v naught, the strength of the potential. Huh? Okay. So how to do it? What I will do, I will just expand this expression in terms of 1 by u naught. I will have simply an expression in terms of 1 by u naught. Okay? Because u naught is finite, let's say it is large, such that 1 by u naught is small. Got my point? So when it is small, so it will simply give me a small parameter for an expansion. Got it? So how to do it? So what I will do, so you can write this twice ik as e raised power I pi, that's minus 1, and 1 minus twice ik by u naught. Clear? So let's take the log on both sides. Okay, so we expand equation 1 in terms of 1 by u naught. So let's call this as equation 1. So let's take log on both sides. So it is twice ik, that's I pi, plus log of 1 minus twice ik by u naught. What is the expansion of log of 1 minus x? Because 1 by, it is x is small here. Okay? So this is your x and it's small. Clear? So what is that? So it is simply, so let's write k is equal to, so it is simply pi by 2 plus 1 by 2i. Got it? So what it will be? It will be minus x, so twice ik by u naught, minus x square by 2, so that is 1 by 2 twice ik by u naught whole square minus 1, x cube by 3 and so on. Clear? So we'll go only up to order of 1 by u naught square because 1 by u naught is small. So what you got? So you have got again a transcendental equation. Okay? So minus 2 and 2 cancel. So what you get? I only k by u naught. Okay? So then minus and minus is plus. So 2 is 4. So it is something k square by u naught square. Why? So 2 is here. 2. Clear? Okay. Got it? Now we have to solve this very equation. It's again a transcendental equation, but in a perturbative manner. What I will do, I will just take the linear order of this very equation and solve for the linear case. So let's figure out the solution in linear case. You will do it actually in the numerical method, how to solve such equation. Let's only consider this linear part. Okay, let's consider. So what you are having? So k is equal to pi by 2 minus k by u naught. So what you got? So it means you are getting k is equal to 1 plus 1 by u naught, that's equal to pi by 2. What is your k? Pi by 2 into 1 plus 1 by u naught whole inverse. Clear? So let's make a binomial expansion. It's pi by 2 into 1 minus 1 by u naught minus 1 by u naught square minus 1. Clear? Got it? Let's substitute it back. Okay? So therefore, my k is equal to pi by 2 minus 1 by u naught. What is your k? So it is pi by 2 minus pi by 2 u naught. Okay? So I will not consider u naught square here. It will be u naught cube. Huh? Okay? And dash dash dash. Then you are having 1 by u naught square. K square will be equal to square of this thing. So I will consider only pi square by 4 minus plus dash dash dash. All other high terms. Huh? So what that is equal to? So it's pi by 2 minus pi by twice u naught minus plus pi by 4 u naught square. And what you are having, there should be an I. One I factor we are missing. Yes, this I we have missing. So this I is multiplying this object. So you are having an I here. Clear? I is in the denominator. So I square it's plus something. Okay? Is it clear? Huh? Is it clear? Yes, there is an I staying here. Eh? This twice I. Okay? So I and I cancels. 1 by 2I. So 2, this I multiplies this expression. I square is minus 1. It's plus here. So it will be what? I. So it is simply minus I. Okay? So plus I pi square by 4 u naught square. Got it? So what you got? So I think there is a minus change somewhere. You have to check it. Eh? Somewhere we are having a minus problem. Okay, so what you ultimately you got? So this is your real part of the objective. Okay, plus order of 1 by u naught cube. Clear? So let's say this is your k naught. K is equal to k naught minus. So this should be actually minus here. Eh? It should be minus. Eh? So somewhere you have to check. Is there whether this
minus.
yes. So it is already plus. So yes. This already plus. How? Okay, look here. So it is I square is minus and this minus is plus. Clear? And then you are having I, it will go up. Okay, great. So it's I times this gamma. So what is our gamma now? Pi square by 4 u naught square. So what is our lifetime? Lifetime of the particle. So have you got the idea what I am saying? So you are having a metastable state existing within the double Dirac delta potential, and its lifetime is what? Okay, twice h cross by tau. So how much is tau? So that's related to gamma. So it will be something. So let me write it. It is something 4m u naught square by pi cube h cross plus something order of 1 by u. Okay, and because this u naught square will go up. Okay, so much on. Okay. So what is your u naught? Now tell me. So 4m by pi cube h cross. What is u naught? So that is twice m. Okay, v naught by h cross square. So what it will be? 4 m square v naught square by h cross raised power 4. So that means, so this lifetime of this very state is 16 m cube by pi cube h cross cube. Okay, and v naught. Okay, now if V naught, the first argument, what we did in the first case, if the potential is very large, Okay, the width of the potential is very large, or this weight factor is very large. Let's say V naught tends to infinity. What will happen to this tau? Lifetime goes as infinity. That means it is a stable state. It becomes actually a stationary state. So much out? Have you got now the idea what we have done from the one-dimensional scattering problems? So we have got how to deal with the reflection and the transmission coefficients. We have dealt with the bound, how to calculate the bound states, as well as how to figure out the resonance states and the lifetime of those resonance states. Got it?
Yes, sir.
So let's now move to the general scattering theory. So this, what we have done till now, it was all restricted to one dimensions. Okay. So the theory, what we'll be doing now, that is true for one dimension as well as the higher dimensions, three dimensions as well. Right? So how much time is remaining?
10:23. 2 minutes.
So just start.